Okay, I've already screwed this up so many times. Take 20. I don't know what it is. Okay, I'm going to try to get this done. Although the bell's going to ring before I'm done, and I've got to go to a faculty meeting, I'm going to try to get this done. I want to talk to you in this screencast about how to interpret graphs of position versus time and velocity versus time. Two very important skills that we're going to be using again all the time in physics. Let's go. So we often look at motion graphs in physics, and when we do that, the x-axis is always going to be time in seconds, but the y-axis varies. In this case, it's a position graph. So it's position measured in meters, and it could be velocity in meters per second. We'll talk about that next. But here's the thing. We usually put 0 at the midpoint, and we have negative values here and positive values here. So let's just go ahead and populate this graph. Let's just say a car drives from left to right, and an observer is standing here. So this is where the car is at different points in time. Each of these are 2 seconds apart. So at time t equals 0, that means when the person first started recording the position of the car, it was 30 meters to their left, right? So we call that negative 30 meters of position at time t equals 0. 2 seconds later, the car is now 20 meters away to their left, so negative 20. 2 seconds after that, at t equals 4, it's 10 meters to their left. At t equals 6 seconds, it's passing right in front of the person, so 0 meters away. 2 seconds later, at time t equals 8, it's 10 meters to their right in the positive direction. And then 2 seconds after that, it's 20 meters away in the positive direction. So I get these points here. Now, there's 2 things we often do in physics. When we have data points like this, one thing we do, one thing we don't do. One thing we do, we draw a line of best fit. One thing we do not do, we do not play connect the dots. Okay, when you have your FRQ at the end of the year, you're going to have to draw a best fit line. You do not want to play connect the dots. Now, here's what's really one of the most important takeaways from today, and that's when you have a position versus time graph, the slope of this line, that is your velocity. Why? Because I'm changing position as I move from point to point on this graph, and change in position over time is the definition of velocity, is displacement over time. So since this has a positive slope to it, I know it has a positive velocity. Let's just look at how we calculate this. Velocity is the change in position over time, and the position certainly changed over time. So delta is always final minus initial. So let's just take the final value of 20, take away the initial value of negative 30. 20 minus 30 is 50, divided by 10 seconds it took to achieve that change. I get a velocity of 5 meters per second. I get the same thing if I took a smaller segment of it. In this case, this is 20, this is 10, this is 2 seconds. I still get 5 meters per second, no matter how small the segment, since this slope did not change. The velocity is going to be the same at all points. Now, what we can do then is we can look at this, and qualitatively we can say, hey, I know both of these objects are traveling in the positive direction, and I know the red one has a steeper slope, so therefore it is going faster. It has a higher magnitude of velocity, and they both have positive direction of their velocities. So if I went ahead and calculated, I'd see, well, the V1, it went from 10 to 60 in 5 seconds, where's in 5 in 10 seconds, so it got 5 meters per second. And if I do the same thing for the blue one, it went from 40 to 60, so it was only going 2 meters per second. So the red one is going 2.5 times as fast as the blue one. So again, the slope tells me which way the object is traveling. So I look at this graph here, I can tell the blue one is traveling in the negative direction. It has a negative slope. So even though its position is in the positive direction from the observer, it is traveling in the negative direction. If you keep going, you're going to end up negative for me, right? So the negative slope means traveling in the negative direction. You have a negative velocity. A positive slope means you're traveling the positive direction, and you'll eventually get there if you keep going. So the slope, a positive slope, means you're traveling the positive direction, even if you have a negative position. And if you have a negative slope, you're traveling the negative direction. Okay, as shown by the math there. Okay, I'll let you look at that later. Sorry, I didn't think about that. Okay. Now, what if you have a slope of 0? Well, the slope of 0 means you're not moving, right? So if I look here, 40 minus 40, well, that's a 0. It's negative 60 minus negative 60, that is 0. So this object is parked 40 meters to the right of me. This object is parked 60 meters to the left of me, okay? Now, what if the slope doesn't stay constant? If the slope is constant, the velocity is constant. So I look at this blue one here, and I can calculate its velocity. I see the velocity is traveling at constant positive velocity. All right, but let's look at this red one. Now, and this is a skill you need to work on. I look at the very first part of this graph. You know what I see? I see a slope, an instantaneous slope that's essentially 0. That tells me this red one started from rest. And as time goes by, it becomes more and more and more negative. So I can tell it's speeding up in the negative direction. But if I look at the purple one, I can see, you can go ahead and grab that. When I look at the purple one, I notice is that it starts off fairly steep. It did not start at rest. If I look at the first part of it, it looks like, yeah, that's about 10 and about half a second. So it's probably going 10 divided by 0.5 is going 20 meters per second. Okay, but I notice as time goes by, that slope becomes less steep. That means it's slowing down, it's slowing down, it's slowing down. And about t equals 7 seconds, it's the slope goes to zero. It stopped moving. Now watch what happens next. Now it starts getting a negative slope. So it's really something you need to get into your head is that when an object reaches a velocity of zero, that means it's going to change direction usually. It could either stop, but often what it does is just changes direction at that point. So I start off at positive 20, I slow down to zero, and now by the time I get here, I have a negative slope of 20. I have a graph here. In this case here, I just have this. The object starts here at 60 meters. It goes to negative 40, and it ends up here at positive 10. So what I want to know then is four things. I want to know what is the average velocity over the 15-second time interval, and what is the instantaneous velocity at times 2 seconds, 6 seconds, and 14 seconds. Let's go. So if I want to find the average velocity over that time interval, I just find the total displacement. Remember, it's always final minus initial. So the final was positive 10. The initial was positive 60. So 10 minus 60, that's negative 50 divided by 15. That's negative 3.5 meters per second. So if I should draw a line between here and here, the slope would be negative 3.3. So it's traveling. Every second it's going 3.3 meters in the negative direction on average. At time t equals 2 seconds, right here, what is its instantaneous velocity? A lot of times kids are like, how am I supposed to find that, Mr. Simpson? Easy. You just look at the area around it. Okay, this slope is constant here. So I say, well, what is the slope of this? Well, I'm just going to find the slope by saying negative 40 minus 60 divided by 5 seconds. It's going negative 20. So since the slope didn't change, I know this whole time it was going negative 20. So at time t equals 2 seconds, it was going negative 20 meters per second, 20 meters per second in the negative direction. At time t equals 6, you know what? I don't even need to do any math here. I can look at that and say, well, that's flat. That's stop. That is the velocity there is zero. If you want to do the math, fine. Negative 40 minus negative 40 is zero. Zero divided by 5 is still zero. And now here it's traveling this way. So when I get to this point here at 14 seconds, I see that this slope is positive. And if I say, well, I'm just going to say
Attention
10
students, the
minus
school
negative
buses
40,
will be
that's
leaving in
50 divided
5
by 5,
minutes.
that's 10
Please
meters per
get on the
second in
buses
the
now.
positive direction. Now let's talk about velocity versus time graph. So velocity, you got to be careful. So when I see velocity, that's meters per second. So this is not telling me where I am. This is telling me how fast I'm going. And again, I'm going to put time in seconds here. So when I look here, I see this red line here says this object was traveling at a constant speed of 15 meters per second in the positive direction the whole time. This object here was traveling at 30 meters per second in the negative direction the whole time. Now, this object is going half the speed of this one, or conversely, the blue one is going twice as fast. The magnitude is twice as much, but it's going in the negative direction. So it's worth noting that negative does not mean less. Negative is telling me that the direction it's going. Now, we're going to start very quickly starting looking at objects that are accelerating, meaning they're changing their velocities. We'll save that to our next lesson after this one. But when that happens, our velocity changes over time. So most of physics, velocity is going to change over time. And when it does, we're going to see something like this. I start off with a velocity of negative 30. I end up with a velocity of positive 15, it looks like, okay? So for today, though, we're not going to worry about the slope of it. I just want you to understand that if as time goes by, if my velocity is getting closer to zero, I am slowing down. Okay, don't say, well, it's less negative. No, the negative just switched direction. I'm moving 30 meters per second in the negative direction. Now I'm only moving 20 meters per second in the negative. Now I'm only moving 10 in the negative. Now I'm moving negative 1. I mean, clearly 1 meter per second is slower than 30. It's just I'm still traveling in the negative direction. When I get to here at 0, I'm not moving. And at this point here, I'm starting to move faster and faster and faster in the positive direction. All right, so just please keep in mind, as we approach 0, we are slowing down, regardless of the slope of the line. An approach of 0, as you get closer to 0, you're going slower. And last thing I want to talk about is how we can use the area under the graph here. So area under the curve is something we're going to do a lot. You know, if you take calculus, you call that integrating it. We're not going to have to integrate functions here, but we are going to have to look at graphs with straight lines usually. And we're going to have to, and you definitely have to do this on your AP test a bunch of times. You have to calculate what the area under the curve is. And the first thing I want to ask you is, what does the area mean? So the area is just going to be this times this, right? That's how you find area, right? Right. So x times y. So if this is meters per second and this is second, if I multiply meters per second by seconds, what do I get? Well, I get meters. right? Because the seconds cancels out. So I just say, oops. So I'm just going to, wait, what just happened here? Okay. So I'm going to do here is I'm going to say, look, I'm going to measure from here, from the line to 0, not to the bottom of the graph. This goes to infinity. I measure from here to 0. So I'm going to say I have 20 times 15. So 20 meters per second times 15 seconds. That means the displacement of this object in this time, it moved 300 meters in the positive direction. That's what it tells me, because this is a positive value. So it displaced in the positive direction. What if I had something like this, though? Well, in this case, the object is slowing down. It was going 20 and it ended up going 0. So I didn't have a constant velocity the whole time. I can still figure out the displacement I'm finding in the area. I've just got to be a little bit careful here. So in this case, the trick to do is this. Imagine a rectangle that goes from here to here. So I'm just going to bound this by a rectangle. That rectangle would be 20 times 15, but this bisects it, cuts it in half. So I'm going to divide it by 2. So 20 times 15 divided by 2, since it cuts it in half. And the displacement of this one was half as much as it was before, 150 meters. Okay, thanks for watching. I'll see you in class.